Welcome everybody to this new lecture of our paper number 3rd, Waves, Oscillations and Acoustics. And in today's lecture, we will continue our discussion about the solution of the differential equation of a forced harmonic oscillator. And this is the situation in our previous lecture. This is our differential equation, and we try to solve this differential equation by the application. This is the general solution of this differential equation. This is my equation number 3rd, which is the differential equation of a forced harmonic oscillator, and this is the general force, which is the combination of this force. This is the combination of this force. This first term is the real force, and this second one is the imaginary part of this force. So this is actually the combination of these two forces. And when the force like this is applied on a damped harmonic oscillator, its amplitude is maintained and the oscillator behaves like a forced harmonic oscillator. Okay. तो एक जर्नल केस के द्वारा हम इस डिफरेंशियल इक्वेशन का सॉल्यूशन हमने प्राप्त कर लिया था, और वो सॉल्यूशन इस तरह का था, गिवन बाय इक्वेशन नंबर 8. इक्वेशन नंबर 8 हम इक्वेशन नंबर 3 जो हमारी डिफरेंशियल इक्वेशन है उसके कॉरस्पॉन्डेंस में सॉल्यूशन प्रोवाइड कराती है. ओके. और चूंकि हमने इनिशियली ये कंसीडर हम करके चले थे कि इस तरह का जो फोर्स F इक्वल्स टू F नॉट e टू द पावर आयोटा ओमेगा टी, इस तरह का फोर्स कॉम्बिनेशन है दो फोर्सेस का जो इक्वल्स हैं F इक्वल्स टू F नॉट कॉस ओमेगा टी एंड द सेकंड वन इज द F नॉट साइन ओमेगा टी विद आयोटा. ओके. दीज आर टू फोर्सेस F नॉट कॉस ओमेगा टी एंड F नॉट साइन ओमेगा टी. तो इस डिफरेंशियल इक्वेशन का जो सॉल्यूशन इक्वेशन नंबर 8 हमें दे रही है वो एक्चुअली एक जर्नल सॉल्यूशन है. अब उस जर्नल सॉल्यूशन का हम स्पेशल केस डिस्कस कर रहे थे और हमने ये कंसीडर किया था अगर फोर्स इस तरह का हो, मीन्स फोर्स रियल हो, तो सॉल्यूशन भी रियल होना चाहिए. और वो जो सॉल्यूशन हमारे पास आया था निकल कर वो कुछ इस तरह का था. जो सॉल्यूशन हमारे पास आया था निकल के वो सॉल्यूशन कुछ इस तरह का था. और अगर फोर्स के साथ इस सॉल्यूशन की हम कंपैरिजन करें तो आपको ये बिल्कुल क्लियरली दिख रहा होगा कि ये जो फोर्स है जो कि एक रियल फोर्स है और ये सॉल्यूशन भी रियल है, तो ये फोर्स ओमेगा टी, दिस F इक्वल्स टू F नॉट कॉस ओमेगा टी, यहाँ कॉस के जो एंगल में है वो ओमेगा टी है और यहाँ कॉस के एंगल में है ओमेगा टी माइनस 5 प्लस पाई बाई 2, मीन्स समथिंग सब्ट्रैक्टिंग फ्रॉम ओमेगा टी. Something, this quantity is subtracting from the angle of cos omega t. That means the force which driven the oscillator is always leads by an angle of this minus 5 plus pi by 2 by the oscillator or by the forced harmonic oscillator, because this is the displacement y of a forced harmonic oscillator. So we can say from these two equations that the force which driving the oscillator is always leads to the oscillator by an angle of this minus 5 plus pi by 2. और कला में इतना आगे है, इस एंगल से कला में आगे है, हम ये बात कह सकते हैं. यानी जिस फोर्स के द्वारा प्रणोदित दोलक दोलन कर रहा है वह फोर्स, वह बल प्रणोदित दोलक के आयाम से कला में आगे है, अग्रगामी है. दिस इज द राइट वर्ड, अग्रगामी, लीड्स. ओके. और इसी बात को हम एक दूसरे वे में भी कह सकते हैं कि प्रणोदित दोलक प्रत्यावर्ती बल से कला में माइनस 5 प्लस पाई बाई 2 कोण से या एंगल से, इतने डिग्री से कला में पीछे है. सो दिस इज द रिजल्ट एंड दैट इज माय टारगेट इज दिस. My target is this. Let us discuss the two cases when F equals to F naught cos omega t and F equals to F naught sin omega t. We will show that the driven oscillator is always behind the driven force. Always behind the driven force in phase. not in velocity, not what, no, not in phase. Driven oscillator is always behind the driven force in phase. That is the thing we proved here. Okay. Now the second case. Let us consider the second case when the driven force is this, F equals to F naught sin omega t. चूंकि ये एक इमेजनरी फोर्स है, यानी जो एक्सटर्नल फोर्स है उसका एक इमेजनरी पार्ट है, तो जो सॉल्यूशन होगा डिफरेंशियल इक्वेशन का वो भी एक इमेजनरी सॉल्यूशन ही हम कंसीडर करेंगे. सो लेट अस डिस्कस दिस केस. ओके. क्योंकि फोर्स कॉम्प्लेक्स है, फोर्स इमेजनरी है, तो जो सॉल्यूशन होगा डिफरेंशियल इक्वेशन का, जो हमें देती है इक्वेशन नंबर 9, ये इक्वेशन हमें देती है जनरल सॉल्यूशन ऑफ दैट फोर्स, जनरल सॉल्यूशन ऑफ द डिफरेंशियल इक्वेशन. तो इसमें से चूंकि हम रियल फोर्स को अब नहीं अप्लाई कर रहे, कॉम्प्लेक्स या इमेजनरी फोर्स को वहां अप्लाई कर रहे हैं, तो जो सॉल्यूशन होगा डिफरेंशियल इक्वेशन का वो भी इमेजनरी ही होगा. दैट इज द सॉल्यूशन by applying that force of this type, the solution of the differential equation number 3 will become like this: y is equals to minus f naught over omega zm cos omega t minus phi. And look at here, this is my equation number 12. Okay, and I can write this equation in this form: f naught over omega zm sine, because this omega t minus phi plus phi by 2, sine theta plus theta, this sine theta minus pi by 2 is given in this form. Okay, this cos is converted into sine, and that's why this minus sign is absorbed here. This minus sign is absorbed here. So this equation number 12 can be written in this form. Okay, because the force applied here is complex, the solution will also be complex. Okay, now see here, the driving force is this in this situation. Solution is this, driving force is this, solution is this, and again see that here is f equals to f naught sine of omega t. That is, in the angle of sine here is omega t, and into the displacement equation, into the angle of sine, check the angle of sine, here is omega t minus phi plus pi by 2. This. Okay, again these two equations shows that driving force which drive the oscillator is always leads to the oscillator by an angle of minus phi plus pi by 2, minus phi plus pi by 2. That's why, and that's the result we want to obtain, that the driving force is always leads to the driven oscillator, okay, by an angle of minus phi plus pi by 2, and the amplitude is also this is the value of y equals to y naught, and what is y naught? The maximum value of displacement, and the maximum value of displacement is known as amplitude. That's why this term f naught over omega zm is here represented the amplitude of a forced harmonic oscillator in this situation. Okay, so this is the solution. These are the solution of the differential equation number 3. Okay, the solution of this differential equation. Okay, in the steady state, into the steady state. Okay, this is the steady state behavior of a forced harmonic oscillator. When the oscillator is starts oscillates with the frequency of driving force. Okay, not with its natural frequency. Okay, when the oscillator oscillates with its natural frequency, this is the case of transient state or the transient behavior of the oscillator. That behavior of the oscillator is known as transient behavior. Okay, so these are the solutions of the differential equation we obtained in the case of a forced harmonic oscillator. These are the solutions, and these are the special case. Okay, when the force is real, when the force is imaginary, but the result is same. Either the force is imaginary or the force is real. The driven force is always leads to the driven oscillator. That's the tagline or result of this whole calculation. Okay, now moving to the next one is change in amplitude with frequency. Amplitude में change देखना है with frequency of a driving force. एक driving force के amplitude में किस तरह का change आता है with respect to frequency. फ्रीक्वेंसी ज़्यादा होगी क्या होगा, फ्रीक्वेंसी कम होगी ज़्यादा होगी कब होगी. क्योंकि हाँ हमारे पास दो फ्रीक्वेंसीज हैं अवेलेबल. एक वो फ्रीक्वेंसी जिससे ऑसिलेटर ऑसिलेट करता है ट्रांजिएंट स्टेट में, यानी ऑसिलेटर की नेचुरल फ्रीक्वेंसी, और एक फ्रीक्वेंसी है हमारे पास ड्राइवन फोर्स की फ्रीक्वेंसी जिससे ऑसिलेटर ऑसिलेट्स करता है स्टेडी स्टेट में. तो उन फ्रीक्वेंसीज की वैल्यू किस तरह से एम्पलीट्यूड पे इफेक्ट करती है वो हमें इस टॉपिक में सीखना पड़ेगा. ओके, और जो रिजल्ट्स यहाँ हम ऑब्टेन करेंगे वो हम फर्दर यूज करेंगे. हम जो रिजल्ट्स यहाँ से ऑब्टेन करेंगे अपनी फर्दर डिस्कशन के लिए, उन रिजल्ट्स का हम यूज करेंगे आगे के डिस्कशंस के लिए. है कि आगे के डिस्कशन में जब आप क्वालिटी फैक्टर, बैंड विड्थ एंड रेजोनेंस, शार्पनेस ऑफ रेजोनेंस ऑफ ऑसिलेटर, इस तरह के जब टॉपिक्स स्टडी करेंगे तो वहाँ फिर हम इन रिजल्ट्स को यूज करेंगे. इन रिजल्ट्स को हम वहाँ यूज करने वाले हैं. ओके, सो लेट अस सी दिस. The displacement of a forced harmonic oscillator when driving by this force F equals to F naught cos omega t is this. The solution of that differential equation. If this force, when the driven force is this, F equals to F naught cos omega t. जब ड्राइवन फोर्स इस तरह का हो तो जो सॉल्यूशन आता है वो डिफरेंशियल इक्वेशन का वो हमें कुछ इस तरह का मिलता है. y इक्वल्स टू एफ नॉट ओमेगा जेडम साइन ओमेगा टी माइनस फाइव, जहाँ जो जेडम है आप ये जानते हैं मैकेनिकल इम्पीडेंस है ऑफर्ड बाय द ऑसिलेटर एंड इट्स मैग्नीट्यूड इज गिवन बाय दिस, फाइव इज दिस. ओके, where the constants have their usual meanings. Okay, R is damping constant and mass of the oscillator as stiffness or spring constant of the oscillator, where the constants has their usual meanings. Okay, now because this is the magnitude of mechanical impedance and this is the phase between the oscillator and driven force, so let us substitute 2b is equals to r by m, our substitution, and omega naught square is equals to s by m into equation number 2. This is my equation number 2, which gives me the magnitude of the mechanical impedance of the oscillator. Okay, so Zm is equals to m by omega. Why m by omega? Put these values there. Okay, the value of r from this equation is 2bm. Okay, 2bm, and it's not 2bm, it's r by omega. Okay, and omega, look at here, our first differential equation. No, it's s by m. Okay, it's s by m. Okay, and omega naught square by equals to s by m. These are, तो ये दोनों रिजल्ट्स मुझे यहाँ रखने हैं और उससे ये वाला सॉल्यूशन मुझे मिलता है। कैसे, वो देखेंगे। देखिए, यहाँ से जब मैं r का वैल्यू कैलकुलेट करता हूँ तो मेरे पास आता है 2bm। ओके, एंड ओमेगा नॉट स्क्वायर इज इक्वल्स टू s बाई m। दैट मीन्स यहाँ से मुझे s का वैल्यू निकालना है और यहाँ से मुझे r की वैल्यू निकालनी है। तो जो r वैल्यू यहाँ से देगा मुझे, जो r की वैल्यू यहाँ से मुझे मिलेगी, दैट इज r इक्वल्स टू 2bm, और जो यहाँ से मुझे s की वैल्यू मिलेगी, दैट इज s इक्वल्स टू ओमेगा नॉट स्क्वायर m. Now put these two values into this equation number 2. We have this Zm equals to m by omega, because there is no omega in this term. Okay, let us solve it somewhere else. Okay, let us solve it somewhere else. We have these terms. Okay, give me 1 minute only. Okay, let us solve this equation somewhere else. This is my rough paper and I want to solve here this equation. This equation on this paper. Okay, so let us solve it here. We have Zm is equals to root, this is my mechanical impedance, r square plus omega m minus s by omega whole square. Okay, and we have 2b is equals to r by m and omega naught square equals to s by m. This is my two substitution. So let us solve this equation here. Okay, so let make me some magnification. So this is my mechanical impedance, magnitude of the mechanical impedance, and this is my substitution. So calculate the value of r from here. We have 2bm from this equation, and calculate the value of s from here. We have omega naught square m. Okay, and now put these two values, that is r equals to 2bm and s equals to omega naught square m, into this equation. Then we have this r square equals to 2bm, that is the square of 2bm. The square of 2bm gives me 4b square m square. Okay, and plus omega m minus the value of s, and the value of s is this omega naught square m, omega naught square m over omega, this is whole square. Okay, और अब मैं, आप ये देखते हैं यहाँ से इस इक्वेशन से आप ये देखते होंगे कि देखिए m स्क्वायर यहाँ भी है, m यहाँ भी है और m यहाँ है और ये होल स्क्वायर में है, तो जब यहाँ से m बाहर आएगा तो वो m स्क्वायर ही होगा और m स्क्वायर इस टर्म के साथ भी है, तो मैं यहाँ से m कॉमन ले लूँ, तो यहाँ मेरे पास बचेगा 4b स्क्वायर प्लस ओमेगा माइनस ओमेगा नॉट स्क्वायर ओवर ओमेगा, ओके, होल स्क्वायर। अब मैं यहाँ से इस टर्म से ओमेगा कॉमन लेना चाहता हूँ, बाहर ओमेगा कॉमन लेना चाहता हूँ, चूंकि ये स्क्वायर के साथ टर्म है और ओमेगा यहाँ आएगा तो 1/ओमेगा स्क्वायर बाहर आएगा और फिर से मैं जब इसके स्क्वायर रूट से बाहर लाऊंगा तो ये टर्म मुझे बनेगी m/ओमेगा बाहर, ओके। अब चूंकि ओमेगा इस टर्म के साथ नहीं था तो और ओमेगा को यहाँ से कॉमन लिया गया तो ओमेगा की मल्टीप्लाई हो जाएगी यहाँ, सो 4b स्क्वायर ओमेगा स्क्वायर प्लस ओमेगा की मल्टीप्लाई यहाँ भी होगी ओमेगा स्क्वायर माइनस ओमेगा नॉट स्क्वायर होल स्क्वायर। दिस इज माय रिक्वायर्ड सॉल्यूशन or substitution, not solution. This is my required substitution. By substituting these two values, the value of R and the value of S, we have get this equation. And now look at the solution of the equation now. The mechanical impedance of the oscillator is this. Zm is equals to m/omega root 4b square omega square plus omega square minus omega naught square whole square in the square root of this value. And this is the same value as we acquire on our rough paper by substituting these values. Okay, look at here. Look at this equation and now look at this. Look at this equation and look at this equation. m/omega root 4b square omega square plus omega square minus omega naught square whole square. Okay, this equation, this. And now look at this result. m/omega root 4b square omega square plus omega square minus omega naught square whole square. Okay, omega naught being the natural frequency of the oscillator. जहाँ जो ओमेगा नोट है वो नेचुरल फ्रीक्वेंसी है, क्योंकि हमें वेरिएशन जो देखना है वो एम्पलीट्यूड का देखना है फ्रीक्वेंसी के साथ, यानी चेंज इन एम्पलीट्यूड और वेरिएशन ऑफ इन एम्पलीट्यूड विद रेस्पेक्ट टू फ्रीक्वेंसी ऑफ द ड्राइविंग फोर्स ओके। एंड हियर इज ओमेगा नोट इज द नेचुरल फ्रीक्वेंसी ऑफ द ऑसिलेटर. Okay, now from equation number first we have, this is my equation number first, this is my equation number first, this is my equation number first, which gives the value of the displacement of the forced harmonic oscillator. Okay, when the driven force is F equals to F naught cos omega t. So this is the solution of the differential equation, and we have this value of Zm now. Zm equals to m/omega root 4b square omega square plus omega square minus omega naught square to the power square. Okay, अब ये वैल्यू यहाँ से उठाइए Zm की और इक्वेशन नंबर फर्स्ट में यहाँ रखिए. Then the displacement of the forced harmonic oscillator is become like this. Y is equals to F naught omega, omega is same. The value of Zm is this. So put here this value. m/omega root 4b square omega square 4b square omega square plus omega square minus omega naught square omega square minus omega naught whole square. And because there is sine omega t minus phi, then this equation will also have sine omega t minus phi. Okay, so this is now my condition. The displacement is this. Omega is cancelled with omega, so we are left with the solution of this differential equation when the force is F equals to F naught cos omega t. Okay, so this is my solution of the differential equation, and the driving force is y equals to f equals to f naught cos omega t. So this is the displacement. Okay, and let us look this equation. This equation gives me the displacement y equals to f naught over m, because omega is cancelled with omega, root of this quantity and sine of omega t minus phi. So let us write f naught over m is equals to small f naught. This y is equals to small f naught, which is the value of f naught by m. Okay, same root square root quantity, sine omega t minus phi is same. Okay, so only the substitution is this: f naught over m, capital F naught over m is replaced by small f naught. Okay, now substituting f naught over this quantity of square root is equals to a. Then this equation number 4, will become in this form: y equals to a sine omega t minus phi. This is my equation number 5 of this topic, and this whole quantity is the amplitude, or you can say it as the displacement amplitude of the oscillator, or you can say it as forced harmonic oscillator. This is my amplitude. Okay, and now I want to, because the topic is this, change in amplitude with respect to frequency of driving force, not of oscillator, but of driving force. Okay, and I know that the frequency of the driven force is omega in this discussion. Omega naught is the natural frequency of the oscillator, and omega is the frequency of driving force. So actually I want to see the variation of amplitude with respect to omega. That means I want to see the variation of a, small a, with respect to omega. That is simply, it is the battle between small a and omega. Small a and omega. Okay? Simply the battle between the amplitude and the frequency of the oscillator. Sorry, not oscillator, the frequency of the driven force. Okay, so we shall study the behavior of displacement amplitude, this quantity. Okay, this is the key factor in this derivation, or in this topic. This expression of a is the key factor. Okay, so let us discuss the variation of displacement amplitude with driven force frequency, that is omega. Okay, so we shall study here the behavior of displacement amplitude, that is the quantity a, versus driving force frequency. That's why I called it the battle between the amplitude and the frequency of the driving force. And the frequency of the driving force is considered to be as omega. So there are 3 stages. First at low frequency, second as resonant frequency, and third is at high frequency. Okay, so let us discuss first case at low frequency. When look at this expression, when omega, that means omega is the frequency of driven force and omega naught is the natural frequency of the oscillator. जब driven force की frequency oscillator की natural frequency से बहुत कम हो, that's why this is named as low frequencies. At low frequencies, जब driven force की frequency oscillator की natural frequency से कम हो, तो क्या होगा? That is the driving force frequency is very much less than the natural frequency of the oscillation, then this expression of A, which is called as displacement amplitude, is given by this expression. Okay, and because omega is very, very less than omega naught, so omega is tending to 0. Omega is tending to 0, which means this term 4b square omega square is also tending to 0, and we neglect omega square with in comparison to omega naught square because of this condition. Omega, which is the frequency of the driving force, is very, very less than to the natural frequency of the oscillator. That's why if omega tending to 0, which suggests me that this quantity 4b square omega square is also tending to 0 or equal to 0. And the comparison between these two quantity, because omega square is omega is less, very, very less. That's why omega square is very, very, very less than omega naught square. That's why we can neglect this term 4b square omega square and omega square into the denominator, that is the square root term which is written into the denominator. Then here is 4b square omega square is negligible, and omega square is also negligible in the second term, that is the whole square term. So the displacement amplitude becomes F naught is same over this is 0, we are left with only this. So omega naught square to the square is cancelled with the square root. So we are left with only omega naught square. So omega naught square. Okay, and value of F naught. Look at here. Small F naught is capital F naught over m. That is now force per unit mass. This is small f naught is simply force per unit mass. This is the maximum value of force or driven force, F naught. Because the force of this type, F equals to F naught cos omega t. Okay, cos suggests that it is a periodic form like sine wave, periodic force. Omega frequency t time, and F naught. What is F naught? The maximum value of this force. Okay, that's why the small f naught here, this small f naught is the force per unit mass, or the maximum force per unit mass, you can say it. So put the value of f naught, small f naught is capital F naught over m, and the value of omega naught square. Look at here. The value of omega naught square from here is S by m. So put there. So omega naught square is S by m. So put here. M is cancelled with m. So this is F naught over S. Okay. Which suggests that the displacement amplitude A of the displacement amplitude of the oscillator is quite independent of the frequency of driven oscillator, because this is simply the battle between displacement amplitude and driving frequency of force. Displacement versus driving force frequency, but there is no term like frequency. Only we have F naught, that is the maximum value of force which is applied to the oscillator or the driven force, and S is the stiffness constant. So this is the constant. This is also a constant, or can be considered as a constant. Okay, so look at this result. At low frequencies, in the limits of low frequencies, the displacement amplitude is quite independent of the frequency of driven force. That is the result we acquire. First result. At low frequencies, the displacement amplitude is quite independent of the frequency of driven force and is approximately constant. You can say it as approximately constant. So in verbally you can say it that at low frequencies, driven force frequencies, at low frequencies, the amplitude of the force oscillations depends upon the driving force F0 and stiffness constant, but is independent of frequency. जिसके साथ हम वेरिएशन देखना चाह रहे थे उसके साथ ये वेरी नहीं करता लो फ्रीक्वेंसी लिमिट्स में. यानी जो एम्पलीट्यूड डिस्प्लेसमेंट है ये फैक्टर लो फ्रीक्वेंसी लिमिट्स में फ्रीक्वेंसी पे डिपेंड ही नहीं करता. किसकी फ्रीक्वेंसी? ड्राइविंग फोर्स की फ्रीक्वेंसी. ओके, दिस इज द फर्स्ट रिजल्ट वी एक्वायर फ्रॉम दिस डिस्कशन, दैट इज in the low frequency limits the amplitude displacement of the oscillator is not or quite independent of the frequency of driven force. Okay, now talking about the second situation. The second situation is at high frequency. At high frequency means the frequency of the driving force is very greater than the natural frequency of the oscillator. This is my next situation, and the relation is same, expression is same. The expression which gives me the displacement amplitude is same. Okay, this equation is same. So let us discuss this case. At high frequency limits or in the limits of high frequencies, when omega, which that is the frequency of the driven force, is very greater than the natural frequency of the oscillator. Okay, so look at this equation, because this time omega is very less than omega is very greater than omega naught. So this term is sustained now, and in this term, because omega is very greater than in comparison to omega naught, so omega naught can be neglected. Omega naught can be neglected in this case. Okay, so if because the driven force frequency is very greater than the natural frequency of the oscillator. That is physically you can say that the transient state of the oscillator is of very small time, and the oscillator is continuously oscillates in the steady state. So put this equation here. Omega, if omega is very greater than omega naught, then this term is sustained, and into this term the omega square is sustained and omega naught square can be neglected. Okay, so if you neglect this term, this equation of which gives the expression of amplitude displacement of the driven oscillator or forced harmonic oscillator is converted into this equation, F0 over 4b square omega square plus, because omega naught square is neglected, so omega squared to the square, that's why omega to the power 4. Okay, and this can be written as this, F0 over omega. So why? If the damping is very small. This is the condition of this equation. Either this equation is satisfied. If the damping is very small, that is B is very small, because this is the damping coefficient. So this term can be neglected because B is very small. If damping is very small, then this expression is valid. If damping is not as small as we consider, then this is my required expression for amplitude displacement. Okay, so if B, that is the damping coefficient, is very small, so that 4b square omega square can be neglected. Okay, then the final expression is this, but with the condition if B is small. And if B is very high, Then in high damping limits, we study in our past unit that there is no oscillation type thing. Okay, there is no oscillation type thing. That is, oscillation cannot occur in the high damping situation. Okay, so as omega tends to infinity, A tending to 0. Why tending to 0? Because A is directly inversely is to omega square. Inversely to omega square. That's why when omega tending to infinity, A tending to 0. That is, amplitude almost approaches to 0 as the driving force frequency becomes very large. तो amplitude approximately 0 हो जाता है जब ड्राइवन फ्रीक्वेंसी बहुत ज्यादा हो जाए. दैट मीन्स ओमेगा इनटू द लिमिट्स ऑफ इंफिनिटी, which is not the practical case. Okay, practically it is not possible to tending that omega tending to infinity, but this is an special case. Okay, special case you can say it. Now to the third situation, that is at frequency of displacement resonance. This is a very interesting case, and the results we acquire from here is very interesting also. Okay, so we here discuss the case of when omega is very, very less than omega naught. Second case, when omega is very, very greater than omega naught. Third case is when omega is omega naught. That is, the frequency of the driven force is equal to the natural frequency of the oscillator or forced harmonic oscillator. And this is known as the displacement resonance. Okay, let us see this. In this case, omega equals to omega naught. This is my equation of amplitude displacement. Okay, F naught over root 4b square omega square plus omega square minus omega naught square equals to 0. Oh, sorry, to the power to the square. Okay, and in this limits, in this condition, omega equals to omega naught, this term omega square minus omega naught square will vanishes. Okay, so this term gives me 0. Then we are left with 4b square omega square, which is the whole square of this value, 2b omega. So whole square is cancelled with the square root, and we are left with A, the amplitude displacement in this situation when the frequency of the driven force is equal to the natural frequency of the oscillator. The amplitude is this. Amplitude is this form. And look at here. The amplitude is directly proportional to omega, because you can say it that F naught is approximately constant, 2 is constant, B is also constant. Then if B is constant, then A, the amplitude, the displacement amplitude is directly inversely proportional to 1 by omega. And in this situation, as we discussed earlier, that amplitude displacement is inversely proportional to the square of the frequency or square, and but here is directly proportional to omega. That is, at omega equals to omega naught, and the frequency of the driven force is equal to the natural frequency of the oscillator, the maximum amplitude, this, is inversely proportional to the damping coefficient B, and also inversely proportional to the frequency of the driven force. Okay, theoretically, if B is equals to 0, अगर B की वैल्यू यहाँ 0 हो जाए, यानी डैम्पिंग बिल्कुल ना हो, बिल्कुल डैम्पिंग ना हो, तो यहाँ तो फ्री ऑसिलेशन हो जाएंगे. ये तो सिंपल हार्मोनिक ऑसिलेशन बन जाएगा जब डैम्पिंग बिल्कुल ना हो. देखिए, सिंपल हार्मोनिक, डैम्प्ड हार्मोनिक और फोर्स्ड हार्मोनिक में डिफरेंस क्या है? सिंपल हार्मोनिक नो डैम्पिंग इफेक्ट, डैम्प्ड हार्मोनिक डैम्पिंग इफेक्ट, फोर्स्ड हार्मोनिक it tries to overcome the damping effect. The third situation, simple harmonic no damping, damped harmonic there is damping, forced harmonic tries to overcome damping. That's so if B is tending to 0, then simply A is tending to infinity because A is inversely proportional to B. B is 0, A is infinity, एम्पलीट्यूड इन्फिनिटी. यानी अगर डैम्पिंग 0 हो जाए तो जो एम्पलीट्यूड्स हैं ऑसिलेटर के वो इन्फिनाइट हो जाएंगे. बिल्कुल ये सिचुएशन इसके अपोजिट है. Whenever damping is present, the displacement resonance takes place at a frequency of omega equals to omega naught square minus 2b square can be proved as. Whenever डैम्पिंग इज प्रेजेंट, ये केस तो ऐसा है कि जब डैम्पिंग है ही नहीं. बी टेंडिंग टू 0 सजेस्ट दैट देयर इज नो डैम्पिंग और डैम्पिंग टेंडिंग टू 0. बट बिकॉज इन अवर प्रैक्टिकल केसेस देयर इज नो सच केस when there is no damping effect present in the oscillations of any system, so practically it is not possible. So if there is damping, in practical case, if there is damping, then the displacement resonance takes place at a frequency of omega equals to omega naught square minus b square 2b square, and which can be proved as. For amplitude A to be maximum, dA by d omega should be equal to 0. This is my trigonometric trick. Okay, and displacement equation, displacement amplitude is given by this equation. Okay, displacement for amplitude A to be maximum, dA by d omega should be equal to 0. This is that is the thing we learned from the trigonometric relation, maxima and minima. And displacement amplitude is this. So let us differentiate this equation with respect to omega. D by d omega of A. D by d omega of A. Let us do this. This is simply a mathematical calculation. So d by d omega of A has this value. So when we differentiate this quantity with respect to omega, we have this result. Minus f naught 4 omega square minus omega naught square plus 8b square omega over 2 4b square omega square plus omega square minus omega naught square to the power square to the power 3 by 2 is equals to 0. Because dA by d omega equals to 0. We want to find the maximum value of A. Okay. So this term will be equals to 0, so denominator comes to the 0 and multiplied to the 0 onto the right hand by cross multiplication, and we are left with this. Because f naught cannot be equal to 0, so we are left with 4 omega square minus omega naught square, this term plus 4b square omega equals to 0. The numerator is equals to 0, and from this equation omega square minus omega naught square, this term is equals to minus 2b square. From this equation we can acquire this result. Okay, and what is the value of omega square from this equation? What is the value of omega square from this equation? Okay, the value of omega square is simply omega naught square is comes on to the right hand side, will becomes positive, and minus 2b square is already there, so the value of omega square will become omega naught square minus 2b square. And the value of omega is simply the square root of this quantity, square root of this quantity. Okay, and this can be written as in this form, because taking omega naught as common, omega naught is common, so 1 minus 2b square over omega naught square. Okay, and on putting the value of b here, we have the value of b is this 2b equals to r by m. Okay, so b is r by 2m simply. So put here the value of b. Because b is r by 2m, so the expression for frequency omega, which is the frequency of driven force, is equals to omega naught square root 1 minus r square over 2m square omega naught square. Thus the maximum displacement amplitude or displacement resonance, the maximum displacement amplitude situation is known as displacement resonance, takes place at a frequency slightly less than omega naught. Okay, the natural frequency of the oscillator is given by this or this or this. In other words, the resonant frequency of the driving force omega is slightly less than the natural frequency of the omega naught, because this omega equals to omega naught square minus 2b square. Okay, and if I can write this equation as this if this 1 minus something, very small value, and the square root of that value is very, very small. So if this is very small value, then omega is approximately equals to omega naught. Omega is approximately. So the situation of displacement resonance, जब displacement बहुत ज़्यादा हो, उस सिचुएशन को हम डिस्प्लेसमेंट रेजोनेंस कह रहे हैं. इन अदर वर्ड्स, रेजोनेंट फ्रीक्वेंसी ऑफ द ड्राइविंग फोर्स ओमेगा इज स्लाइटली लेस देन द नेचुरल फ्रीक्वेंसी ऑफ द डिस्प्लेसमेंट ओमेगा नॉट. ये इक्वेशन मुझे ये बता रही, और इसको प्रूफ करने का ये तरीका था. मैंने एम्पलीट्यूड को मैं ये कहना चाहता हूं, मैं प्रूफ करना चाहता था कि जो डिस्प्लेसमेंट रेजोनेंस है, अर्थात डिस्प्लेसमेंट रेजोनेंस का क्या मतलब है, ये सिचुएशन जब ओमेगा इक्वल्स टू ओमेगा नॉट हो, अर्थात जो ड्राइवन फोर्स की फ्रीक्वेंसी है वो ऑसिलेटर की नेचुरल फ्रीक्वेंसी के बराबर होगी, तो उस सिचुएशन में डिस्प्लेसमेंट रेजोनेंस होगा, यानी डिस्प्लेसमेंट मैक्सिमम होगा. रेजोनेंस की सिचुएशन आप पढ़ते आए, अनुनाद. तो डिस्प्लेसमेंट रेजोनेंस का मतलब है डिस्प्लेसमेंट मैक्सिमम होगा. और इस सिचुएशन में जो फ्रीक्वेंसी होगी ओमेगा, विच इज द फ्रीक्वेंसी ऑफ ड्राइवन ऑसिलेटर, वो कुछ इस तरह की होगी. और इस बात को प्रूफ हमने कैसे किया, इस इक्वेशन से. और ये इक्वेशन क्या सजेस्ट करती है मुझे, क्योंकि आप ये देखिए इसके राइट हैंड साइड में 1 माइनस समथिंग, तो कितना बचेगा, पॉइंट्स में बचेगा, और उसका स्क्वायर रूट कैलकुलेट कीजिए और भी छोटी वैल्यू आएगी. और इसका मतलब ये है कि ओमेगा में और ओमेगा नॉट में एक बहुत स्लाइटली डिफरेंस फ्रीक्वेंसी है एक दूसरे से. इसका मतलब तो रेजोनेंट फ्रीक्वेंसी है ड्राइविंग फोर्स की ओमेगा, वो बहुत ही छोटी है, स्लाइटली लेस देन द नेचुरल फ्रीक्वेंसी ऑफ ओमेगा. दिस इक्वेशन सजेस्ट मी दैट. Okay, so that's all for now, and meet you into the next one to continue this topic from here. Okay, so thank you for now.